All right, folks. Well, I think we'll get underway and welcome to this little webinar, which will go for somewhere between an hour and a half tonight. And there's two other sessions to come. There's quite a lot to get through, as you'll judge from how long it's going to take us to get through it. I would welcome questions on the way through. I'm not sure how we're actually going to do that. So I think we've got Chris and Kelly helping me at the moment, and they'll be keeping an eye on the chat. So if I see something jump up in the chat, I'll also answer it if it's appropriate at that time. Otherwise, all the questions will be recorded or captured, and if not answered this week, then answered next week or the week after. So I'd like to make this as interactive as we can. So I'd like to, get questions and make it interactive so that you can get out of it everything that you need to get. All right, well, we'll get underway. I wear two hats tonight. The first is my RCS hat, and RCS sort of started down this track quite a long time ago, and then 16 years ago, CarbonLink was spun out of RCS in order to really do a fair bit of work on carbon and soil carbon, and so CarbonLink is focused totally on working out how to measure and get projects underway for soil carbon. So I started in this for one basic reason, is I believe that agriculture flounders and mines its resources because consumers will not pay the full price of food. And agriculture has been mining its land resource now for 8,000 to 12,000 years. And I think sometimes in agriculture we get a little bit uppity about how much landscape the miners impact, but I can tell you that agriculture impacts far greater area than miners will ever touch. And so I believe that if consumers can't and or won't pay the full price of producing food, and my observation is that it's either the ecosystem or the humans that are producing the food that pay the rest of that cost, and especially the ecosystem, and that's been paying it for a very, very long time. So carbon or environmental credits can actually provide a mechanism to return additional income back to landholders. And so that's the reason that I got into this in the first place. 17 years ago, I had this, I guess now looking back on it, I'd call it a brain fart, thinking that it'd be a great idea to get farmers produced for adding carbon to soils. Little did I know how difficult that would be and how long it was actually going to take. So I think that, my philosophy is really similar to this, in that we have obligations to future generations, and adding carbon and natural capital to our ecosystems is one very good way of getting that in there. So over the next 3 weeks, we're going to cover quite a lot of topics. We're going to look at where carbon fits within the ecosystem, a little bit an introduction to soil organic carbon and some of the science there, how we go about measuring it and the economics of doing it. And then, well, that's probably where we'll get to tonight. Next week, we'll be looking at what is a carbon project, what are some of the rules, and then some case studies, and maybe even a look at CO2, friend or foe. And then the third session, we're going to be spending a lot of time on practice change and how do we go about sequestering carbon. So this is a little test that I like to throw out there. There's two aggregators come along and they've offered you two different prices. One is going to charge you $2,250 to baseline your project, and the other one's going to charge you $20,000. The first one's going to take only 5% of the credits, and the second one wants 18% of your credits. Now, if I was asked to ask a group of farmers, landholders what they would choose. 90% will go for the cheap option. A little bit further down tonight, I will actually look at what it will have cost you to take the cheap option. So I look at our ecosystem as a pie. And I think for the last 8,000 years, as I mentioned, we've been shrinking the size of this ecological pie. Carbon's like the center of this ecosystem. We've got ecosystem services, we've got things like the water cycle, soil health, energy flow and biodiversity are parts of this pie. Everything within this pie is interlinked, and we cannot separate one of those from the others. Although tonight we're going to separate one out, and that's carbon. But while it's possible to degrade the ecosystem, it's also possible to regrow every component of that ecosystem once we have a fair idea what we're doing, what management we need to put in place to reverse what's been happening to our ecosystems, which means that we can grow that little piece in the middle as well, being carbon in the ecosystem. So what is carbon? It's a form of energy, whether it's in the food that we eat, it's a source of energy for us, for livestock, for virtually everything gets its energy from carbon in one form or another. And that energy is basically comes from creating heat or creating energy in some other form. And when we look at it from a human perspective, carbon is the beginning and end of all life. We start as a speck of carbon and we'll finish as a speck of carbon in the ecosystem. So it's absolutely critical to all life. But, you know, if you look at the television at night and you see these smokestacks pumping up water vapor into the air, and you would think that carbon is a linear process in that we're pulling carbon out of fossil fuels or coal, etc., burning it in vehicles and power stations, and then all of that carbon goes straight to the atmosphere. However, in agriculture, we actually work within what I call the short carbon cycle. So that fossil fuel comes from the long carbon cycle, whereas in ag, we work within the short carbon cycle. So the old carbon cycle, the long one's been started about 375 million years ago when Mother Nature developed photosynthesis. At the time Mother Nature developed photosynthesis, there was 7,000 parts per million of CO2 in the atmosphere. Photosynthesis has pulled that down from 7,000 parts per million to about 240, round about at its lowest point. So the carbon cycle that Mother Nature created when she created photosynthesis is still going today. So in the photosynthetic side of the carbon cycle, we've got birth, growth, reproduction. And in that side of the equation, carbon is taken from the atmosphere and ends up through photosynthesis in every living thing. But on the other side of the carbon cycle, we've got oxidation. And oxidation is the process of death and decay. And so what we need to do is leave behind a little bit every time carbon goes around in that cycle. Preferably in soils, but we can leave it in vegetation as well. But really what I want to focus on over these next few weeks is soil carbon. So the equation is very, very simple. Sequestration is the difference between photosynthesis and oxidation. So we can either increase photosynthesis while holding oxidation constant and we will get more sequestration, or we hold photosynthesis constant and we reduce oxidation and we will end up with more sequestration. It's not our goal to try and slow down the carbon cycle. If anything, we would like to see more carbon cycling in and out of every living thing. So, and then there's what I call the fast carbon cycle. And that is the carbon cycle in and out of our plants on a daily basis or a weekly basis, monthly or annual basis. And we'll look more closely at where that carbon actually goes and where it comes from. Within the carbon cycle itself, so this is the amount of carbon that goes in and out of everything every year. There's an estimated 100 gigatons. That's 100 billion tons of carbon. Now, this is carbon, not CO2. So in the cycle, so that means in and out of everything every year, we've got 100 gigatons. In the atmosphere at the moment, it looks like it's around about 878 gigatons of carbon. And back in 1890, it was 800 gigatons of carbon. So right now, we've got an estimated around about 412 parts per million of CO2 in the atmosphere. And back in 1890, we had around 280 parts per million. So since that time, a bit over 200 years, we've actually added around about 78 gigatons. So that's 78 billion tons of carbon to the atmosphere over that period of time. In all the vegetation on Earth, there's around about 550 gigatons of carbon. In the top metre of soils, there's 1,824 gigatons of carbon in the top metre. So if you add up the atmospheric carbon plus all the vegetation on Earth, it does not equal the amount of carbon in the top metre of our soils. Our annual emissions, and this was a year or two ago, I think this was the 2019 annual emissions, I think 2020 was fairly similar, was around about 9 gigatons. That is from burning fossil fuels and manufacturing cement. Now, there are other emissions over and above that, but those are the two that basically come from those. The 9 gigatons basically comes from those two sources. There's still 10,000 gigatons of carbon stored in known reserves of fossil fuels, of which we're using up around about 9 gigatons a year, or at least emitting about 9 gigatons a year from those sources. There's an estimated 1,000 gigatons of carbon in the surface of the ocean and 37,000 gigatons of carbon in the deep ocean. So to me, it's not a very big ask globally for us to take 9 gigatons of carbon and put it away in an 1,800 gigaton storage. So it's relatively simple maths, but much more complex than that to actually achieve. But if we look at that 9 gigatons of carbon that's going into the carbon cycle each year, not all of that lands in and stays in the atmosphere. The latest figure I've seen from NASA is around about 25 to 30% of those annual emissions remain and build in the atmosphere. The rest will end up in the ocean, vegetation, and in the soils. So that's the big picture, if you like, in carbon on an annual basis. Two completely different estimates here on how much carbon's been lost from soils over the last 12,000 years, and one is 1,000 gigatons, and more recently there's been an estimate of 133 gigatons. So either way, it's a lot of soil or carbon from soils that have been lost over the period where we've been doing agriculture. So when we look at carbon trading, there are two things that we can actually trade or do things with. The first is an avoided emission. So an avoided emission is lowering fuel, lowering our methane emissions, lowering our electricity use, lowering our fertilizer use, etc. And lowering emissions is like saying, well, there's a cliff in front of us there somewhere. And what we're going to do now is instead of being in top gear, we're going to put this car in third gear and we're still going to drive towards the cliff. Sequestration is the opposite to that. Sequestration is we're taking carbon dioxide out of the atmosphere and storing it either in permanent vegetation or in soils. And certainly in soils, we can store it for a very long period of time. So the one I'm going to talk about a lot more rather than vegetation, again, as I said, I will focus more on sequestration into soils, but we will also cover a little bit more on emissions as we proceed. Just to put emissions in context, these are 3 projects at the moment that are on their way to being credited this year. So you look at the graph over here. So the first property has sequestered over a 5-year period 140,000 tonnes of CO2. The second one there is around 170,000 tonnes of CO2, and the third one just under 120,000 tonnes of CO2. Here's their baseline emissions. Baseline emissions were somewhere between 700 tonnes and 1,500 tonnes of CO2 a year. Project emissions, not very far off, but 2 properties have had higher project emissions. And then the net credits that will be sold this year is around that sort of 80 to 100,000 tonnes on 2 projects, and the smaller ones back at about 60,000 tonnes. So those are sort of credits will be issued from those projects this year. But I want to just focus a little bit on the emissions. And if we look at the blue project here, they have actually lowered emissions from their baseline to their project. Sadly, they get no reward for lowering emissions. Then when you look at the other 2, the orange one and the grey one, both of those, their emissions have increased during the project period, which is a 5-year period from 2016 to 2021. Now, those emissions over and above their baseline emissions are subtracted from their total emissions, that total sequestration rather, to get to net credits. So there's no benefit to lowering your emissions, but there is a penalty which is removed from your net credits for emissions that exceed baseline. I'm going to talk a lot more about that in the session next week. But really the thing I wanted to point out was that there is so much focus on emissions, but when you put emissions up against total sequestration into soils only, and a lot of these guys were also sequestering carbon into trees, but that wasn't measured. The average emissions across these projects is around about 8% of the sequestration. So the emissions are certainly very low relative to sequestration. So I'll just pull up there and see if there's any questions in the chat or Q&A. So Q&A, righto. So who are the current extension providers from the public and private sector for the carbon farming industry? Well, I think there's a new carbon aggregator starting up almost every day at the moment. The space is becoming very, very crowded. There's not many in that space that have been around for a long time. I think there's 3 organisations that have been around for a long time. In terms of public extension, there's a little bit of extension through the NRMs and a little bit of extension through the departments of ag. At this stage, I think most of the extension's being done by the aggregators. How was the sequestration achieved in these projects? These were grazing projects, and the sequestration was achieved by intensification of grazing management. I will go back into these projects in a lot more depth later in this series. If you sell an ACCU to a third party, does this place an incumbency on your property? No. That's the short answer, but I will again come back into these regulations a little bit later. So there's 3 projects that I have data on there at the moment. There's a 4th one that didn't sequester carbon, so that might give you a bit of an idea. So they have submitted to the regulator a nil sequestration report. We're about to remeasure that property again, and we know what went wrong the first time, and we'll hopefully correct that
with this next measurement. So there's no penalty for them not sequestering carbon at the moment. So all they need to do is go again and make sure that we've been able to measure the change in carbon as we move forward into the next one. I'll come into the land size as I get into the economics a little bit later. Let me see. Yeah, I was hoping to get to the economics tonight, so I'll cover that one then with some data. Great questions. Thank you for that. So I'll move into the next segment, and there's still opportunities to ask plenty of questions, but we'll move into the next segment. So soil organic carbon itself. So what we have here is soil organic matter, which consists of living organisms, fresh residue, decomposing organic material, and stable organic carbon in the soil. As a rough rule of thumb, we put a line through the middle. About half of that is organic carbon. It's slightly more than that, but as a rough rule of thumb, let's just say it's 50% between friends. And so for the rest of this talk, when I talk about soils, I'm going to talk organic carbon, not organic matter. Now, there's usually questions around, if I put a lot of litter on the ground, will I sequester carbon? Basically, no. Decomposition of organic matter on the surface and in the surface, generally going to lose 60 to 80% of it. Depending on temperature, it could be a lot more than that. So I wouldn't be expecting that you will sequester a lot of carbon by leaving a lot of litter on the soil surface. That's not to say that you do not need litter, and we'll get into that later in the series. You certainly need litter, but for other reasons. So it's root-derived carbon that is the major source. It's carbon that either comes out of roots or is coming from decomposing roots. That's the main source of carbon, and one of the reasons why that's important to us is that carbon is also at depth. So there's two important forms of carbon within the soil. There's what's called particulate organic matter, and there is mineral-associated organic matter. I'll just run through those and compare them. So particulate organic matter is mostly of plant origin, and it's larger particle sizes, generally low in nitrogen. It's vulnerable to disturbance or loss. In other words, because it's still organic, it's much more likely to oxidize. Has generally a higher rate of decay. But one of its advantages is that it continues to accrue after saturation, and I'll come back to that shortly. So the mineral-associated organic matter is a microbial product, and this is the stuff that's more likely to end up as humus. It's generally considered to be less than about 53 microns, which is pretty damn small. It's high in nitrogen, therefore it has a low carbon to nitrogen ratio. Less vulnerable to loss, in other words, much more stable in the soil, lower rate of decay because of that and because of its stability as essentially as organic products. But it does saturate the soil. In other words, you will reach a saturation point at some stage with the mineral-associated organic carbon. So here's some data published a few years ago. And on the left-hand side of this, you can see the mineral-associated organic matter. And you can see that it does tail off across a lot of soils. But that would be around about, so 50 there would be around about 5% organic carbon. And you can see, so somewhere around about 5% organic carbon to higher organic carbon. A lot of soils will actually start to not be able to add more mineral-associated organic matter.
But as you'll see on the right-hand graph, they can continue to add particulate organic matter, but that is less stable than the mineral-associated organic matter. So also there's a difference between grasslands and forests. And the other important bit here is the C to N ratio. So MAOM has a high proportion of soil organic carbon. That's important. POM, the particulate organic matter, has a wide C to N ratio. So we can pick that up on the right-hand graph there. And MOAM, has a narrow, I should say, the narrow carbon to nitrogen ratio. So a wide one here for the POM and a narrow one for the MAOM. So carbon nitrogen ratios are quite critical to us. In other words, adding carbon to the soil, adding nitrogen to the soil is going to be critical to us generally, particularly the MAOM, which is the one we're chasing because of its stability. It's got a narrow C to N ratio, which means that the nitrogen is going to be important in that system to be able to sequester and hold that carbon. So how does carbon get into the soil? Firstly, and the one that most people would be aware of, is decomposition. So we've got a group of bugs in the soil, mostly saprophytic type organisms, which can break down those root systems and consume that organic matter. And they'll be able to turn some of that organic matter into humus, some of it, and particularly closer to the surface, they will turn into organic products which can actually oxidize relatively easily. So we're after deep, large root systems on our plants, and that's going to contribute probably 20 to 30% of the organic carbon that we can add to our soil. By far and away, the most important way of getting carbon into the soil is through what Christine Jones calls the liquid carbon pathway, which is sugars produced by photosynthesis. So those sugars, around about 40% of sugars in a rapidly producing plant, will actually go down to the root system and out into the soil to feed the microbes. We'll get a lot more into that in our third session and how that operates, but essentially what's happening here is the plant is feeding these microorganisms, communicating. Not only is it giving them energy in the form of carbon, but it's communicating to these microorganisms, and it's able to tell the microorganisms what it actually wants brought back to it. So the plant might be hungry for a bit of zinc at the moment, so it can send a message to the biology, grab me some zinc, or it might be phosphorus or calcium or whatever it actually needs. It can communicate that to the biology. And that system under there is highly intelligent. And one of the things that we're very capable of doing is really mucking up that intelligence and getting in the way of nature's ability to operate effectively. So you can see in this slide here, particularly on the right-hand side, so you've got a root down there, and then the root hairs coming out from those roots. Root hairs are microscopic, so when you pull a plant up, you'll never see the root hairs. These are globules of sugars or root exudates coming out of the root hairs. And also during rhizophagy, those root hairs are also exuding bacteria that have had the outer wall stripped off them, along with those sugars and along with some messages going out. So that's a major source of energy for quite a large proportion of the soil biology. Now, if we look at plant production, plant productivity increases as organic matter content and therefore organic carbon increases within a soil. So in this particular experiment here, at 0.5% organic matter, we had virtually zero yield And then as the organic material increased in the soil, the yield went up to about 7 on this particular scale. But what you can see is new carbon in the soil. So I should say that that green line is the yield of carbon in all parts of the plant. So that is the roots, the shoots, the seed, the fruit, etc. But you'll notice that this other line is new carbon in the soil. And you'll see that it breaks away from the pattern of the actual yield of carbon in plant material at around about 2% organic carbon. So at that point, the level of new carbon in the soil takes off and increases at a faster rate. So the question is, where does that extra carbon come from? Because it's not coming from plant material. And the answer to that is it's coming from fungi. So if you, on this particular experiment, the ratio, the fungal bacteria ratio was highly correlated to that new carbon in the soil. So that tells us that carbon sequestration is a function of fungi, not bacteria. So it's not total biology. And in particular, it's the mycorrhizal fungi. So here we've got a root, which is the black bit, and the white bits are the mycorrhizal fungi attached to that root. So they have the ability to go away from the plant, bring water back to it, and bring various nutrients back to it. As they get further away from the plant, they also have an association with phosphorus solubilizing bacteria. So the fungi can also call in the phosphorus solubilizing bacteria, get that phosphorus off them and send that back to the plant if that's what the plant was looking for. But what the mycorrhizal fungi is able to do is stabilize that carbon. So on the outer wall of the hyphae, the mycorrhizal fungi in particular produce a substance called glomalin. And glomalin is the glue that actually holds soil together. Glomalin's critical for aggregation. And it's been estimated that it's around 20%, 27% of stored carbon. It's the super glue in a soil, and we need a soil to be well aggregated. And it's the glomalin that actually creates those aggregates and holds the soil together in aggregated sort of particles. It does break down more quickly in the tropics, and that's the heat. So the oxidation increases with heat. But glomalin itself is 30 to 40% carbon. So this is a really important step in stabilizing carbon within the soil. And it was discovered not that long ago. So on the top row here, you've got soils that are aggregated, and you can see there's, they're like match heads sized bits of soil there, which is the aggregation. When you remove the glomalin from those soils, you essentially end up with bulldust, depending on the soil itself. So this one on the left is classic bulldust. So if we don't have mycorrhizal fungi, then our soils are going to be very dusty, very windy. And in fact, one of the causes of erosion is actually not having enough mycorrhizal fungi and not having enough glue in the soil, and having these fine particles which can actually float away in either wind or water. We need a good soil structure, and it's aggregation that gives us this good soil structure. So we've got all of this pore space, which can hold air, can hold water. If we've got a compacted soil, then we're going to end up with less pore space and less water and less air getting into that soil. And our soil biology, and including our mycorrhizal fungi, most of them are aerobes, and therefore they need oxygen to do their job. So we need a well-structured soil, and again, it's the mycorrhizal fungi that are going to create that aggregation for us using glomalin to produce it. Now, within the soil, there are two basic structures, two forms of colloids. There's the clay colloid, and this is clay colloid under an electron microscope, and you'll see it's got this plating sort of pattern about it. Humic compounds and humus itself is a moving feast. It's one of the reasons why humus is almost impossible to measure. So this is a computer simulation of a humic acid. And you've got all these carbon bonds in there. So if you break or change a few of them, then you've got a different product immediately. And so you can see it's actually a highly complex substance, and that gives it a lot of benefits. So if we compare clay colloids and humic colloids within the soil, clay colloids are mostly negatively charged. They do have a very small amount of negative charge, but predominantly negatively charged. A humic colloid, on the other hand, can be reasonably well negative and positive on the same colloid. So what that does is that gives a humic colloid a lot more strength than a clay colloid. So it can hold significantly more nutrients and significantly greater water holding capacity, and up to 25 times the water holding capacity of a clay colloid. So getting more humus into our soil is actually very critical. So it's got the muscle and the strength compared to a clay colloid, but unfortunately it's also the lightest particle in the soil. So if you've got wind erosion or water erosion, your humic colloids are disappearing fairly quickly. Now, the negative charges on both the humic and the clay colloid attract these cations. So we've, things like manganese, calcium, zinc, sodium, magnesium, iron, hydrogen, etc. So both clay and humus have the ability to hold and exchange those nutrients. But humus has a better potential to hold things like sulfur, boron, molybdenum, nitrates, and phosphorus. But what can tend to happen with the clay colloids, they get hold of phosphorus and some of these things and don't let it go. Whereas the anion exchange capacity of humus is far greater. So let's think about why soil organic carbon is important to us. Many, many reasons. So obviously, as we get more carbon in the soil, we're improving the health of that soil and we're improving its productive capacity. So you're increasing your carrying capacity, your crop yield, etc. You're increasing the water holding capacity. And there's two things here that most people probably haven't thought of, and that is that if you have carbon credits in your bank account, and you reach a couple of crook years where the commodity prices are down, or the rain is down, etc., and therefore your income is down, you can pull those carbon credits out of your ANREU account and sell them in order to pop up your cash flow. So having those credits, not only having the carbon in the soil, will make you more resilient to that drought, but having the credits in your account will also help your business cash flow through those periods. Increased ecosystem resilience, and generally in a lot of systems, lower costs as we get more carbon into the system. So a couple of fun facts here before I come back to some more questions. So a hectare of soil 1 metre deep will weigh anywhere around 12,000 to 15,000 tonnes, and if it was really, really bad, it could be 20,000 tonnes. Now that could contain 70 tonnes of carbon or soil organic carbon. So if the sequestration rate was a tonne of soil organic carbon a year, that would add 6 tonnes of water per hectare per year, and about 80 kilos of circulating nitrogen per hectare per annum as we add that carbon to our soils. But over a 5-year period, we're looking to find a 5-tonne change in a 12 to 15,000 tonne pool. And that carbon will reduce the weight of the pool, which makes it even more complex. So this is not a game for the faint-hearted, I can tell you that. So you've got to be on your game to be able to find a 5 tonne change added to 70 tonnes of soil organic carbon in that massive pool of soil. And generally, this is the way it's measured. So on the left-hand side, you'll see a property here. So carbon mass per hectare in the top 3,500 tonnes of soil per hectare. And you can see it varies from around about, where are we? It's probably 34 tonnes of carbon per hectare, right up to about 48, 50 tonnes of carbon per hectare. And then when we go below that, to the top 14,000 tonnes of soil and soil mass per hectare, obviously the total carbon mass increases. We've got the odd patch there now at over 100 tonnes of carbon per hectare, but our lowest level now is around the 56 tonnes. So getting down at depth and finding that carbon mass within the soil is where the game is at. Now, if we look at clay content, clay is a good water holder. You know, it's great for water holding capacity. So if we had a clay soil or soil that's had, say, 40% clay in it, and only about 1% organic carbon, then that soil would be able to hold around about 30% water. If we have 10% clay in a soil at 1% organic carbon, we've got very little water holding capacity. If we took that same 40% clay content soil to 9%, this is actually an organic matter, 9%, which is 4.5% organic carbon, then our water holding capacity goes up to 70%. So there's no doubt that as we add more carbon to any soil, whether it's a clay soil or not, we're going to increase the water holding capacity of that soil. But in some soils where we have very, very low content, then the only way we can increase that water holding capacity and cation exchange capacity is to get more carbon, organic carbon, into the soil. So I'll pull up there for questions and I'll go back now to where we were. So where are we? I'll go back to that land one again. Ben's question. So what went wrong with the fourth property? How can we make sure it doesn't happen if we sign up for a project? So the issue in that fourth property was actually around soil mass, which I would need one of our scientists to come in and give you about an hour's explanation of how that actually works or how that actually went wrong. But essentially, we didn't collect the same soil mass as we collected in T1, which means that we're going back to that now. We'll make sure second time round that we certainly harvest enough soil to get the equivalent soil mass. But one of the issues with this is that if we go onto a property, and let's say we're coring down to 1.2 meters, and the soil equivalent mass in the smallest, the shallowest. So what we end up, put it another way, what we end up having to use as soil equivalent mass is the soil equivalent mass of the 10% shallowest cores that we actually take. So, and that's a pretty severe sort of way of looking at it, but that's what the methodology says. So there's a lot of traps in this for young players. And let me tell you, there's a lot of young players coming into this game right now that don't have much of an idea what's going on. John, do you have a recommended tool to measure the baseline of the property? We're going to get into measurement very shortly, John. Oops, Daisy. Oops, I took myself there pretty quickly. Yep. So we're going to get into that. Seem to be missing some somewhere. How do I get to them? Get down a bit. There we go. Where are we? In the circumstances where soil carbon is lost, is the farmer liable to pay? The short answer, I think that's the one I answered before. The answer is no, you have time to make it up. Is the purpose of diverse dense cover crops to capture the CO2 respiration lost during decay? No, it's not. The real function of cover cropping is to add diversity to your soil biology, and it's the soil biology that does the work. Stable or unstable organic matter. So stable means that it's going to be less susceptible to oxidation. Unstable means that the air is going to get out and it's likely to return to the atmosphere as CO2. Do the mycofungi have a preference for soil type or conditions? Well, the main condition is that they need like all living things, they need soil, food, water, and air. So we've got to feed them. We've got to make sure they've got water. We've got to make sure that there's oxygen in the soil. And the food they need is sugar from plant root exudates. I measured a lot of soils over the last few years for biology, and from sort of about Canberra through to central Queensland, and I don't think there was any soils that had a decent fungal to bacteria ratio. So our soils generally are deficient in fungi, and that's one of the tricks we've got to learn, is how to get more in there. Do you think ACCU price would drop in years of drought because sellers may flood the market to make up for the financial losses? Yeah, that's a how long's a piece of string question. I think that it will depend on the market at the time. The market is a market. It's going to go up and down, and it's a supply and demand market if that happens during a drought. The other side of that coin is that there's also less carbon credits hitting the market. So yeah, I'm not sure that that actually would be something that I'd never thought of it, but I'm not sure I'd worry about it. Sequestering carbon in soil versus vegetation. I'm going to come back to that one, Linda. Interested in the comments on root exudates on the root hair. Can you manipulate the sugars that are exudated through foliar feeding of plants? A really good question. I suspect that we probably can, because the evidence at the moment, I think, is that plants fed from a foliar system, rather than throwing fertilizer on the ground, I think tend to be more, tend to do better. And if the plant's doing better, then the carbon's going to do better. Can flooding or waterlogging decrease organic carbon? It's unlikely to decrease it, but you won't be adding to it when you've got anaerobic soils. And I will show you one of those projects I just showed you. Had 2 floods during that period, so we'll talk a bit more about that later on. Forests or grasslands store more carbon. I think it depends on your time frame. So if we were to store more carbon tomorrow or over the next 15 years, trees would probably win. If we wanted to store more carbon over the next 50 to 100 years, then soils will win. Would you say, what would is the more common soil health issue which if solved or rectified leads to the highest sequestration rate. I think the biggest issue is air. Too many of our soils have no air. Too many of our soils don't have enough shelter. And too many of our soils, because they don't have enough air, they also don't let enough water in. I'd say generally the structure is probably more important than the chemistry. Although, chemistry, as you would know, can affect structure. So I would be focusing on what we can do for structure. All right, we might just keep moving on there. I'll let. So let's move on now to the sampling question, or how do we measure it? It's certainly not measured the way we measure soils for agronomy. So I'll run you through the process that we use in CarbonLink, and I've now got my CarbonLink hat on. And so CarbonLink offers sort of, I guess from a measurement perspective, two significant advantages. One is what we call our net spatial work, which is the imagery work that's really critical in this, and then the scanning process, which I'll go through all of those processes with you. And net impact is basically the feasibility study, due diligence, and practice change advice up front. CarbonLink currently has the capacity to do 40,000 hectares a month. That is increasing, and within about 18 months, we'll have the capacity to do somewhere between 80 and 100,000 hectares a month. So the net impact, which is the feasibility and due diligence, and this is the starting point for a carbon project. So we're interested in the project areas and eligibility. So what's the land use history, the tenure, etc. We've got to make sure there's no native title on it. You have the legal right to sell the carbon off it, etc., etc. So there's a hell of a lot of detail in that stuff. Then we want to look at the property characteristics, the soil type, clay content, climate, rainfall, and from that we can calculate a sequestration potential. What management practices might be involved? Does the management have the capacity and the interest and ability to change practices enough to be able to sequester carbon? And I think that's actually one of the biggest issues. So then we would then do a net abatement forecast, work out the project costs, what the risks are, and what the methodology requirements are. So that's all up front before you really commit to the most of the project. From there, we're using the smarts of some of our GIS guys, and I think there's 7 or 8 of them on the team now. Several of them have got PhDs in this stuff. And so you're looking at, firstly, sequestration potential, and we've got some very smart tools now for working out sequestration potential. Then there's the carbon estimation areas, which are the areas at which you'll get credited for your carbon credits. And there's a lot of science goes into doing those. And if you get them wrong, you can run into all sorts of trouble. And then stratification. So once we've done the carbon estimation areas, then we've got to break that up again and stratify that according to management practices, vegetation types, and all sorts of other issues. So there's a lot of science goes into get to that bit there. And I'd say on an individual property, there's between 1 and 2 weeks work for some of our PhD guys to get through, particularly those last 2 maps that I've got there. And then we do a sample plan. So this property here on the left, you can see that each one of those dots is where a soil sample is to be taken. Those samples are computer generated, and the moment they're computer generated, they have to be submitted to their geolocation has to be submitted to the regulator. So we can't go out and drill one of those holes before they're submitted to the regulator. And that means they can't be gamed. You can't actually decide, well, there's my sample plan and I'm going to go out later and change them and pick better spots. That's just not possible. And then the CEAs, so this is the sort of what a couple of CEAs look like. They're the areas in which you're going to actually earn carbon credits at the end of the day. There's lots of reasons why you would split a property into different CEAs. One of them might be titles. You might have a couple of different titles and you might want to sell one in the future. So if you wanted to stop a project, you would actually be able to stop one of those and the other one could actually keep going. Stop it for any particular reason. This is the sort of drilling rig that we use. These are purpose built. We can drill to 1.5 meters with this. This one's only going to 1.2 meters. You can see that it's actually very, very fast to drill these holes. So it's about to pull the core out. And always a good idea to put that away before you drive the truck. And so there's the core that comes out of the middle. So again, accuracy here is very, very important. And now the labeling. So we have very detailed systems here. We have stuff on an app, we have stuff on paper, we have stuff written on the core. So that protects you against errors. So time it takes most of the time to go from pulling up to driving away will be around 6 to 7 minutes. And these vehicles can go in some pretty interesting places. So then those cores are taken and put into cold room. So they're kept cold as soon as possible. We have our own purpose-built cold rooms with their own motors and so on, so they can be parked out in the paddock and be able to stay cool. Otherwise, keep near electricity. When those cores come back to the laboratory, they go through these scanners here. So this is some of the equipment on the scanner. So that yellow and orange bit there is a gamma ray densitometer. What that does is shoots a gamma ray across the core. This bit over here on the right-hand side measures that, measures how long it takes those gamma rays to get through. And from that, you can work out the bulk density. Coming down from the top is a camera. Over here on the right, you can actually just see the photographs of that soil core. And then there's a very expensive NIR unit sitting in there, near infrared unit, which measures carbon and moisture in the core. So then that instrument goes right along the core and measures the bulk density, carbon and moisture all the way down that core. So out of that instrument, you end up with all these lines, basically squiggly lines. The top one is the bulk density, and the second one is the densitometer reading, and the second one is the NIR reading. So then we have to convert all of those squiggly lines into actual information, which can be used going forward. That goes into our carbonizer, excuse me. That goes into our carbonizer software, which then does all the calculations. Goes straight to the cloud, where that data is then kept very secure. So this is the sort of information, there's a whole lot of information that is going to be able to come off these scanners. Not all of this at the moment is available. So we're looking at, organic carbon, obviously we can get that at the moment. Soil organic carbon, the carbon fractions, we're in the process of working that out, clay content, cation exchange capacity, all of these things can be done. We don't have all of the equations we need at the moment to do all of those on all soils. So over the next year, that sort of stuff will start to come back to each farmer. So you'll get a massive amount of information on your soils and at depth. The core analysis cost of CarbonLink is lower than basically anybody else, and that's because of the scanning equipment is faster, non-destructive, and therefore works out cheaper. So after we've taken those cores, they've gone through that scanner, they've then gone through carbonizer, they've been calibrated, then analysed, and then mapped back again. And so this is what's called a heat map. And that's the first 3,500 tonnes of soil. So if you look at that, you'll see some really low ones there in the low 20s or the 20s tonnes of carbon per hectare. Highest is up in the 50s. And so that's our starting point, and that's your baseline in the top 3,500 tonnes of soil. So what that looks like is if you're using the old techniques where you're measuring 0 to 30 centimetres and then you're measuring below that, you get two answers. So you get one result that represents the top 30 centimetres of soil, and you get another result which represents the soil below that. What we can get off the scanner is information all the way down the core. So we can pick these patterns, we can pick, where things change. And sometimes something like that little bit there could actually be a crack, or it could be a rock or something that actually just changes the bulk density at that point. So here, the change from 2016 to 2021 was 1.06 tonnes of carbon per hectare in the top 30 centimetres and 1 tonne in the down from 30 to 60 centimetres below that. So it's generally not reported in depths like that, but that's just to show you, that's sort of a rough estimate of what happens. But what is very significant is that the amount of carbon sequestered below 30 centimetres equals the amount of carbon sequestered above it. And we'll talk a little bit more about that when we talk about carbon credits. So again, this is a heat map taken, and this was taken during the drought and the change over about 4 years. And you'll see that the top heat map here is the top 30 centimetres, and the bottom one, the blue one, is below 30 centimetres. And what you can see in the surface, particularly in these soils here, around the red and the orange, etc., those soils have lost carbon. And where the red is, it's lost a lot of carbon in the top 30 centimetres. Now, those soils are black, heavy cracking clays in that area. And they had dieback on that, pasture dieback for most of that 4-year period, and had a drought. So you had bare ground, cracking clay, cracked open, and lost carbon in that patch there. And also some of that around it had lost some carbon. And generally across that site during the drought, that site had lost a little bit of carbon, probably right across that in the top 30 centimetres. But below 30 centimetres, it had actually sequestered carbon right across, except for one little patch there that had lost a little bit of depth. So across that whole area, it ended up sequestering carbon because there was more carbon sequestered below 30 centimetres than there was lost above it. So what we know from some of the literature is that, for example, in South America, greater than 75% of all new carbon were found below 20 centimetres in grassland. And that's pretty much what we're seeing here, is that it can come and go in that surface. Subsoil stocks expected to be more stable. So, that means that so carbon, this is, I guess, a good example of stability to go back to that question earlier, is that in subsoils below 20 centimetres, it has been found to be stable for 1,000 to 2,000 years. And that's because the oxygen can't get at it. And so that's the reason for stability. We're just not getting that oxidation. So I'm going to pull up there for questions and see what we got. So that land one I'm going to come back to later. Recommend tool, we just did that one. Linda, how does sequestering carbon and soil compare to sequestering? We've done that one. More carbon, can rock content negatively impact sampling results or bulk density? It can have an impact because if you hit a rock and you end up with a shallow core and you get too many of those, then you're going to end up only measuring to a shallow depth and you don't have the soil mass that you need. So we really need to be getting as deep as we can get. We need to be getting the soil mass in every round. So that machine of ours will actually punch through reasonable sort of rocks. And we've also got equipment now that can detect gravel and rocks in the soil profile as well. But right now, rock is not assumed to impact on soil carbon. The methodology basically says that the amount of rock you find the first time around should be equal to the amount of rock you find the second, third, or fourth time around. So I'm not sure that I totally agree with that, which is why we're developing new science and equipment now to be able to measure that rock. But I think at the moment, the biggest impact of rock is actually going to be getting to depth. Benjamin Forrester grass, so we did that one. Where am I? What's the soil depth measurement the regulator takes into account? They need measured soils measured to 30 and then below 30. And essentially, the reality is that 30 centimetres and below 30 centimetres is a made-up number, because the reality is when you measure the carbon, it's measured in the top 3,500, 4,500, or 5,128 tonnes of soil per hectare. But so we make up a number that keeps the regulator happy, that's somewhere around 30 centimetres. But the reality is it is a guess. But you do need to do two. The reason for that is that the national accounts are done to 30 centimetres. We are allowed to measure carbon below 30 centimetres, but we have to report it separately. You talk about heat, dry weather, deep cracks, realising carbon oxidation. So what are your thoughts on a carbon project in central Western Queensland on deep cracking clays, a semi-arid climate? At this stage, Ben, I don't think I would be attempting it. I would be wait and see. There is some research going on in those sort of soils, and I think in another 4 years, we'll actually have an answer on that. So the reality is that I think, firstly, from what I know at the moment, and this is not gospel at the moment, it's but what I know is, firstly, we're going to need legumes in those soils to help the grasses in the years when they are producing carbon. Secondly, you're going to have to try and maintain ground cover to stop or reduce the amount of cracking as much as you possibly can. But I know those western soils are pretty hard to stop that anyway. But the short answer, I wouldn't start a carbon project there, a soil carbon project there at the moment, and wait about another 4 years to see what we find out on those soils. What's the hold up? See how to issue ACCUs. Yeah. So those projects were all measured in 2021. It took over a year to work out how to calculate the carbon change. And that was working with the regulator all the way through. And so that was the first holdup. The second holdup has actually been the auditors. One auditor took 6 months to audit the first project. We've since changed to another auditor, but you've got to then teach the auditors. So again, it's slow even going to a new auditor, although the new auditor has been a bit quicker. They're getting through an audit now in probably close to 2 months compared to 6 months. There's another holdup. Then it goes to the regulator. The regulator has 3 months in which to decide how many credits it's going to issue. The regulator also has the right to call for an independent audit. Also, the regulator has independently audited our calculations and found them to be 100% correct. And then if the regulator comes back and asks a question or two, the 3 months with the regulator starts again. So there are many, many reasons for the delays. And it is exceptionally frustrating, not only for us, but the producers involved. Could I share my experience in biochar? If it's introduced in a soil, how does it affect the carbon sequestration? Firstly, you cannot introduce biochar into a carbon project from external to the CEA. If you produce biochar from within that CEA, then you can put it back on the soil. Biochar is considered an emission. That is because the carbon has come from somewhere else. I can't tell you how it would affect sequestration. I don't have any data on that. George, how does biochar impact soil carbon levels? Again, I can't answer that. I don't have any direct experience with biochar. Evan, is it fair to say after 6 consecutive poor rainfall years with well-managed pasture, i.e. destocking, keeping ground covered, there may still be sequestration occurring below 30 centimetres? That would be our experience, although we didn't go 6 consecutive years. The projects that we have now experienced 3 out of 5 very dry. But yeah, not 6 consecutive. So I can't really answer that, Evan. I think it'll depend on the soil, the depth of the root systems, how much rain you did get, because a drought is no rain. And if you've got soils that are responsive to rain, then you will continue to produce a little bit of carbon. And if you can produce that at depth, you may still be sequestering at depth. But we need to measure to really find that out. So particularly on your place, as you know, we need to get up there and measure it. Can we sample deeper? I think you can, but the issue is you're controlled by the shallowest 10%. So we could go and do 2 meters and you know, and your question is there a floor for carbon sequestration? And the data would suggest not. There is literature showing organic carbon down to 5 and 6 meters. And so, and as you would all know, that grass plants and lucerne plants and some legume plants can certainly get their roots down if the soil will allow them to that kind of depth. But there's not many soils where you can get to that sort of depth. You know, you're often pulled up at you know, 1.2 meters or around the meter mark on a lot of soils, and earlier than that on a lot as well. Okay, is there any I've missed there? Where are we? After 3 very good years at our part of New South Wales, should I be cautious baselining now, high carbon levels? I would say that might depend a little bit on how much anaerobic conditions you actually had. So I know that with very wet years, there's been a lot of anaerobic soils, and coming out of this now, a lot of soils are still anaerobic, and so I'd be quite concerned around that. If your soil didn't go anaerobic, the chances were you were sequestering carbon. Is there an advantage in baselining now? That's a difficult one to answer. The short answer is it probably depends on the amount of carbon you actually have in your soil. If your soils are below 2% organic carbon in the top sort of 20 centimetres, then you might as well baseline now, because you've got plenty to go. And as you approach 2% organic carbon, you are moving to that inflection point where the sequestration rate will actually increase with rainfall in future. It is going to be, like, if we go into El Nino years again, that's certainly going to slow it down. But as I'll show you in the real data when we get to that a little bit later, that we have sequestered carbon through the drought. So far there's 6 properties been remeasured, and 5 out of those 6 have sequestered carbon. I don't have the emissions data on some of those, which is why I couldn't put them in the graphs earlier. Is sequestration of carbon linear or exponential? I think they're actually more like a sigmoid curve. So they're slow to begin with. They will speed up when you get to around about that 2% organic carbon, but then they will reach the saturation point, and that saturation point will vary depending on where you are. And the saturation point is going to be in the mineral associated organic matter, but there may still be potential to add SOM, or soil organic matter, to that after that. But that's going to be less stable. In the other side of that, the other answer to that is that it is possible to sequester carbon in soils forever. You just won't get paid for it. So there's a limit to what you can put in a soil carbon, into a soil within a soil carbon project. But over time, what will happen is, as you add carbon to a soil, you're actually going to build soil. So when you reach saturation point, say that's 5% organic carbon, and you've got 5% organic carbon all the way to 1 metre or 1.5 metres, or wherever your sea horizon is, then you're just going to build soil. You're just going to be adding carbon on top of what you already have, and you can continue to take it out of the atmosphere and just keep going. So the soils won't stop. What are the challenges for producers on leasehold land? Leasehold land in WA is a problem. Native title's a problem. Leasehold is a problem. And at this stage, we can't do them. Is there a minimum property size to facilitate? We'll come back to that one. Talking about limits, how long do you think you can sell credits for? Is credit selling a short-term income? I think you're looking at 25 years. I can't see any soils being full within 25 years, unless they're very shallow. And if they're very shallow, then I probably wouldn't even kick it off. What's the rest of that question? I think the credit demand is going to accelerate as we get towards 2050. As we start to reach 2050, who knows? I don't know whether it'll drop off or continue to accelerate, but I think that through the 30s and into the 40s, you're certainly going to be able to sell it.
So due to deep cracking clay and the native grasses that grow there, arbitral grass, down to it would be better to measure as deep as possible. Yeah, that's a really good point on those downs. On the experimental work we're doing, we're only going to 1.2 meters, but that raises a very, very good point. Johannes, Guy Brown's measured 1% organic carbon increase in 1 year using biological amendments. Oops, where did that go? Just lost you. I just lost Johannes's question, so I don't know what it was now. Righto. So we will. How we go for time? No, we're nearly out of time. Just so if there's any other questions, we'll answer those, and then we'll pull up. So the next section I was going to do with economics. So we'll do economics first up next time. And so are there any other questions there that I haven't answered? Land size is one we're going to answer when we get to economics. Should we focus on ACCUs as frequent flyer points, instead focus more on the co-benefits of the ward? Absolutely. I believe that you should be adding carbon to your soil for the production benefits, for the water holding capacity, for the soil health benefits, and treat ACCUs as a bonus. Great point, Nathan, and I appreciate you raising it. Spot on. Jeff, what percent of the sequestration is due to rainfall, and what's the minimum rainfall to sequester carbon? The projects that we have measured got down to about, the lowest one got down to 170 mils running rainfall in 1 year, not much higher than that in the next year. So certainly over those drought years, they were in the 200 to 300 mil range. And certainly I couldn't tell you whether we sequestered carbon in those years, but we certainly held. I suspect we did, because I don't think we could have got the amount of carbon we got without some sequestration in those years. The minimum rainfall, I don't know whether I can really clearly answer that well at the moment, Jeff, but I would hazard a guess at 500 if you push me for an answer. And hopefully we can get it lower than that when we get more data moving forward. So the Gabe Brown question, is that rate of sequestration that Gabe got possible in Australia? I would suspect so, in the right areas. So one of the advantages Gabe has is a cool temperature. So the things that are going to affect sequestration rate are temperature. So the higher the temperature, the hotter it is, the lower your sequestration rate's going to be. The higher the rainfall, the better your sequestration rate is going to be. Clay content is important in your soil, so there's a range in there that's very important. And overriding all of that is the management. So I would say that it will be possible to do that on some soils in cool areas with clay content, good rainfall, and very, very good management. And by that, I would say very, very good grazing management and multi-species cover cropping in a soil that's chemically balanced. So yeah, I'd expect we'll find that, but it will need everything to go right. Any left? Just the ones around property size. Okay, so we'll hold them over next week, because I don't want to go past our stop date. You've all stayed up long enough as it is.
So thank you all for coming on board. So this is where we're going to go next, and I will see you next week, and hopefully have a good week in the meantime, and may you get under a little bit of rain if you need it. Not too much if you don't need it.